All right, so let's take a look at 2.4, which deals with symmetry. Okay. So one of the types of symmetry that we'll have is this symmetry to the x-axis. So it says every point on the graph has another point on the graph that is equidistant. So if you just picked to the x-axis, so if you just picked a random point, like let's say we picked this point right here, 4, 2, well, we can tell that the distance from the x-axis is 2. Well, it's going to have another point on the other side of the x-axis that's 2 away also, that's matching. So every point on the graph has another point on the graph that is equidistant to the x-axis. There's lots of things with symmetry across the x-axis. You can find a lot of letters in the alphabet. Here's an example of a reflection that's symmetric across the x-axis. Okay. All right, symmetric to the y-axis. So every point on the graph, maybe I'll pick, I don't know, this one right here. Whatever its distance is from the y-axis, that same distance will have another point. So this is going to be symmetric to the y-axis. And so same thing, we have more letters in the alphabet that have symmetry with respect to the y, like the letter M or the letter A. Okay. And then here's a picture of something where if we drew a line right down, or a line segment right down the middle, you would see that you have symmetry amongst the y-axis. For any point on here, you go that same distance, you're going to get another point on here. Okay. Now this isn't as obvious. Okay, so those other two I feel like are kind of obvious. It's symmetric to the x, symmetric to the y, but this one's symmetric to the origin and might be new to a lot of you. Okay, so the way that this is, it says every point on the graph has another point on the graph that is 180-degree rotation about the origin. So if you picked a point, let's say we pick, let's go with this one right here. If we rotated 180 degrees, so 180 degrees is half of a circle, right? So if we rotated about the origin, half a circle, I'm terrible without a compass of drawing this. Maybe it'd be best if I just drew a circle there. Let's see if that'll make it clear. All right. Yeah, that'll do it, I think. Just put it right there. Okay, let's change the color of this to like a greenish color. All right, so if you look, 180 degree, I really need to get that centered about the origin. You guys are, it's not going to work well. There we go. Okay. So 180 degree rotation is half of a circle. And maybe you can see that from here to here, that really is going to be exactly half of the circle that we rotated. Okay. All right. So another way to think about that, though, is it's going to look the same right side up as it does upside down. Oh, okay. I have to take the whole thing here. Let me do this. Sorry. Okay. I'm going to take a screenshot of it so we can flip it. Probably should have erased that point first, but I think that you guys will get the deal here. All right, and let me do this to get everything back that we had. Oops, it's not going to get everything back. Okay, all right, so this guy back. So take a look at how this looks, right? It's going dipping below the x-axis and coming up, right? If I do flip it upside down, which is 180 degrees, we still have that same goes below the x-axis and goes above. It looks exactly the same, right? So anything that you can rotate 180 degrees, which basically means flipping it upside down, right? From right side up to upside down. If it looks the same, then you know that you're looking at something that's symmetric to the origin. There's another trick for determining symmetric to the origin. If you were to take any point and do two reflections to it, if you were to reflect it across the y, doesn't matter the order, by the way, it would go here. And then if you were to reflect it across the x, it would go here. So rotating 180 degrees is the same as reflecting across both the x and the y. Those two transformations together are equivalent to the one transformation of 180 degree rotation. Okay. So you can kind of see that if we did have an XY axis, you know, make it red. Actually, let's make it bright green. Or, you know what, I'll just twist these upside down, right? All of these, if you look at them, the letter S, or if you look at a card, right? If you flip it upside down, it's still the letter S, and it's still going to be a card. These are all symmetric to the origin, you know, assuming that the origin is smack dab in the middle of this king, and then, you know, right here on the S. Okay. I'm going to type out, because we might use this later, we'll see, that a reflection across the X and Y axis is equivalent to a rotation 180 degrees. Oops, digress. How about degrees? There we go. Okay. All right. So this new word, symmetric to the origin, means 180-degree rotation about the origin. And here's some examples where we could be symmetric to all three. Okay. We can see that if we divided this through the y-axis, it would look the same on both sides. If we divided it over the x-axis, it would look the same on both sides. And if we went and we flipped it upside down, it's going to look the same right side up as it does. Oops, I lost my rotating button. There you go. It looks exactly the same as it did this way. And the same thing would be true of these as well. Okay. All right. So we're going to have ways that we test for symmetry in an equation where we don't have a picture. So we're just looking at the equation and we have to figure out, okay? Now, in order for those to make sense, let's just take a look at a single point, and I think that that's going to help us. So if this point is at, oops, 3, 2, which it is, right? And we have symmetric to the x-axis. Well, this is 2 spaces away. So we would need to go 2 spaces away and put its reflection, okay? And that, the ordered pair for that, is we still went over 3, but now we went down 2. So it's going to be 3, -2. So you can see that the x value changed, right? Okay, signs. The x value, I mean, the y value, sorry. The y value changed signs. Later on, when we're testing for symmetry over the x-axis, guess what we're going to do? If we want symmetry to the x, we're going to replace y with -y. And you can see that in, oops, why is it not doing anything? There we go. You can see that we have y here and we have -y here. Okay. All right, let's go and see. If we're symmetric to the y-axis, still taking the 3, 2 that we had. But now we want to be symmetric to the y-axis. So this distance is 3, which means that we would need to do another 3. So that's going to put its reflection over here. Well, now the ordered pair is going to be -3, but still +2. So this time, instead of the y value changing, the x value changed. Okay. Let me look at the words we used last time so I remember. It just doesn't like that open, huh? The y value changed signs. Okay, so this time we're going to say the x value changed signs. Okay. And so you can see right here, if we want symmetry to the y, we'll replace x with a -x, and we'll get an equivalent equation. Okay, so it's kind of like opposites is the way I like to think of it. If I'm symmetric to the x, then the y will change. If I'm symmetric to the y, then the x will change. Okay, let's look at our last case, symmetric to the origin. So we said symmetric to the origin is 180-degree rotation. Oops, it's a half a circle. And I'm going to attempt to draw this. Let me put where I know it's going to go, just so that hopefully you can see. that half of a circle, right, would put it right where it landed. I don't have the other half of the circle, right? But yeah, let me get rid of all those. I think that made it worse. Okay. Now we said if you can't see 180-degree rotation, that's fine. You just do a double reflection, right? So if we were to double reflect, right, and the order doesn't matter. Let's say we did it over the X first this time. We'd be here. And then if we did it over the Y-axis, 3 spaces, we'd be right here. Okay, so this is 3, this is 3, this is 2, this is 2. And we end up in the same spot, -3, -2 versus 3, 2. So now you can see that what happened is not only did the 3 become a -3, but the 2 became a -2. So both the X and the Y changed. Okay, and that's important because when we go and look at symmetric to the origin, how we're going to test for it, not only do we replace X with -X, but we replace Y with -Y and hope that it produces an equivalent equation. So the key thing is every time it needs to produce an equivalent equation, an equivalent equation, an equivalent equation. So X will change the Y's, Y will change the X, the origin will do both. Okay. All right. So we have 4 examples where we're going to, just from the equation, test for symmetry. Okay. All right. So it says determine whether the graph of the equation is symmetric with respect to the x-axis, y-axis, origin, or none of these. Okay. So let's go ahead and make sure that we write down our plan of attack. Okay. We'll start off by checking for the x. If we're looking at the x-axis, then we're going to put -y for y, right? Then if we're looking at symmetry to the y-axis, we will put -x for x, opposites. And then if we're looking at symmetry to the origin, we're going to do both. And the key is, you always want to ask yourself, does it match the original? That's going to be what we ask every time. All right, so here we go. We're going to go ahead and substitute in -y. Now we want to ask ourselves, does this match the original? That's going to be the thing we're going to ask every time. Does this match the original? Okay. Well, clearly, no. And there's no way to make it match the original here. Okay. All right. So then let's go over here and try substituting in a -x for the x. So this means that we're going to have to do -x times -x times -x. Okay, well, 3 negatives means it's going to stay negative. An odd amount always stays negative. And x times x times x is going to be x cubed. Okay. All right, so does this match the original? Okay. No, this does not match the original, right? Okay, so does this match the original? Off by a sign, huh? Okay, so let's try the origin. Which, by the way, this is going to be symmetric to the origin. This is going to be an example to help us remember even and odd later also. So now we have to do both. We got to do a -y for the y. We got to do a -x for the x. Now you don't have to work hard. We already know what -x cubed is. We did all that work right here. Okay, so it ends up just being -x cubed. Well, now it doesn't match the original right now, but we can make it match the original by multiplying or dividing by a -1. So a negative divided by a negative is a positive, a negative divided by a negative is a positive. So it does match the original. So our conclusion is going to be, it's going to be symmetric to the origin. Okay. Now, if you look at x cubed in its graph, right, I think that you'll see that. So this is a graph you just want to memorize. It's one of our parent functions for this class. I'll put it up and try to bring it up as often as possible so that we slowly memorize it. Okay. There we go. Just going to put this in here so we can see what it looks like. And this is going to be one of those where right side up or upside down. Oops. Oh, that was trippy. Right side up or upside down, that graph looks identical. Okay. So indeed, it is symmetric to the origin. Okay. There we go. Okay, let's try another one. Okay, so I'm just going to copy because if it'll let me, I'm just going to copy this again. It won't let me, so just kidding. I'm just going to type that again. All right. So we want to know if it's symmetric to the x, to the y, to the origin, right? All right, so for symmetric to the x-axis, it's negative y for y. For symmetric to the y-axis, it's negative x for x. And then for symmetric, to the origin, both. All right, let's go in here and test this. Okay, so I'm going to substitute a negative y in for y. So does this match the original? There's just no way for me to make this match the original, huh? All right, let's try this next one then, see if it works. So we're going to substitute in a negative x for x. Well, negative x times another negative x. Well, a negative times a negative, or an even amount of negatives, is always positive, and x times x is x squared. So this gets us x squared plus 5. Sorry. All right, so it matches the original. So it is going to be symmetric to the y-axis. Now, some of you might have known that if you know what the graph of x squared plus 5 looks like. But we'll get into that in a second. We'll come and graph it and we'll put it on here. Okay, symmetric to the origin, we're going to do both. So we're going to put a negative y for y. We're going to put a negative x for x. And we already know that this becomes x squared plus 5 from the math that we just did. And so the question of the day, does it match the original? Original. Oh my goodness. No. Okay. All right, so we only have symmetry with respect to the y-axis. So if I were to graph this, just graph it for you because it's a pretty simple one to graph. It's going to be a parabola that's been shifted up 1, 2, 3, 4, 5 spaces. So it's going to look like this. Whoa, way less shaky. Oh, can't undo the shakiness, guys. But hopefully you can see that we do have symmetry to the y-axis. Here's our y-axis slicing right down the middle, right? This is our y-axis. So that's why we got symmetry for the y. Okay. All right. So we're going to do with the x, with the y, and with the origin. Hopefully you're getting so good that you can fill these in on your own, right? So if we went symmetric to the x, hopefully you remember the y for y. And then for the y-axis, we got negative x for x. And then for the origin, we're going to do both. This might need to be spaced out a little bit more. Let's try it. All right, so I'm going to put a negative y for y. All right, so this clearly does not match the original, right? This is off on this y, and there's no way for me to, even if I FOIL them out, to make a match. If you FOIL this one out, it becomes y squared plus 2y plus 1. If you FOIL this one out, it becomes y squared minus 2y plus 1. So while they're close, they are not identical, right? Okay, so these do, it does not match the original, right? Okay. All right, let's try this one. So we're going to substitute in a negative x for x. Well, we already learned earlier that if I have an even amount of negative signs, so that negative x times negative x, it'll become a positive, and then x times x is x squared. So we can see, hey, this does match the original. So we do have symmetry to the x-axis. I mean, to the y-axis. Okay. All right, now let's check out both. So if we put in a negative x for x and a negative y for y, we know this front part is going to become positive x squared. But this is just like example or part 1 when we check for the x-axis, right? This is not going to match the original because of the negative on the y. Okay. So we only have symmetry to the y-axis. Now this is a circle that we're looking at, and it's been shifted down 1. I'll graph it right now so you can see a little bit better. You guys have seen me graph in circles. So I'm just going to go to a grapher because my graphs are pretty shaky today, right? All right, so this was what, y plus 1, I want to say? Yeah, because we said down 1. Radius of 2. There it is, okay. So this is the picture of what we're looking at. So let's go check and see if that works with what we said. We said it is not symmetric to the x-axis. And I think that we can see that. Like this piece is not the same size as this piece. It's not sliced right down the middle with respect to the x. But this side is equivalent to this side. So we are symmetric to the y-axis. And then as far as symmetric to the origin, no, it doesn't look the same right side up as it does upside down. We have the small piece up here and the big piece down there. If we were to flip it upside down, it would not look like that. Instead of it being small up top and big in the bottom, it would be the big one on the top and the small on the bottom. So it does not look exactly identical. Okay. All right. All right. So we're going to go ahead. Now I'll do this one visually first, because if I give you something this easy, which by the time we do 2-5, you'll totally be able to do this fast, okay? The graph of this, and we've referenced this before, you guys, that an absolute values of v. Well, this would be a v shifted down 2 spaces, 1, 2. So it's going to look something like this. So we are going to have symmetry with respect to the y. Boom, I'm done. I can answer that so fast if I'm thinking visually. So a lot of students always tell me I hate graphs, you know, I'd rather just like do the numbers and stuff. But as you get into higher math, I feel like thinking visually really helps out. It really helps out in trig. It really helps out in calculus. And even as you get higher and higher and you take some of these classes, being able to think spatially, 3-dimensionally even, is really going to be helpful. And knowing graphs is going to be super helpful, just on call, being able to like throw it up there. In calculus, we do like disk and washer and all these different things where you have to put a graph up pretty quickly because then you're going to rotate that graph around an axis. Okay. So try to like the graphs. If you're somebody who doesn't like them, just go in there, flashcard yourself, get them down solid. So that way you have them on call and it'll make the rest of the class easy. Look how fast we answered this question versus all this work we're about to do now to check. Okay. All right, we're still going to do it because for those of you who like to solve algebraically, and this one has a little twist that we need to know. Okay. All right, let me change this to 36 font really quickly. Okay, so we know that for the x-axis, we do negative y for y. For the y-axis, we're going to do negative x or x. We got this opposition going on, right? And then for the origin, we're going to do both. Give myself kind of a lot of space there, and I think I actually need it for the middle one. Okay, so if I substitute in a negative y for the y, I think it's pretty obvious that this does not match the original. It's off on the y value. Okay. There's certain things my hands do not want to type. I remember when I used to teach geometry, I always typed angel instead of angle, like all the time. In my notes, it was littered with angel. All right. So for the y-axis, so in order for us to be successful on this one, there's just a little something that I'm going to talk about really quickly that we're going to use, okay? We're going to use this property that the absolute value of x is the same as the absolute value of negative x. That's a property that we're going to use, okay? Property of absolute values. Now, you could just check it really fast if you were like, does that work? You know, you plug in 6 and you substitute in negative 6. Well, the absolute value of 6 is 6. And the absolute value of negative 6 is also 6 because absolute values turn everything positive because they mean the distance, and distances are always positive. Okay, so we're going to need that for this. So I'm going to substitute in a negative x for the x, okay? Now, I have a lot of students who will be like, cool, then that's just going to make this x minus 2. And that's technically wrong, okay? That's not true. Consider this. I mean, so we're wondering, does this equal this is the question, right? Can I just like take the negative sign off of it and be like, cool? But we can't, because what if x itself is negative? We'll use 6 again, why not? Okay. So I plugged a negative 6 in for this x, which means I have to plug a negative 6 in for that x. Now, if you look at the left-hand side, we know that these two negatives here are going to make a positive, and then the absolute value of 6 is 6. Meanwhile, this guy is going to stay a negative 6. So it does not work in the case when x is negative, okay? So this is actually not true. So don't write that down. So that's where this property comes into play. The absolute value of negative x, it's the same thing as the absolute value of positive x. So we're just going to go ahead and write this, and we'll reference that property right here. But the absolute value of negative x is the same as the absolute value of positive x, okay? All right. So, and what I'm going to do is let me just like put a cloud around this guy. So we know that we've talked about him, so you don't do something like that because I can see myself doing it. All right, so does it match the original? Yeah, it does, right? Okay, so that makes this symmetric to the y-axis. Holy moly, I need to choose a smaller font for sure. Let me go and see what size 36 does to this, you guys. Oh, that's perfect. Okay. All right, so now we're going to substitute. We know the answer is no to this because we have the picture right in front of us. This is not going to be symmetric to the origin, but let's do the math. We're going to put a negative y for y. We're going to put a negative x for x. Negative y has to stay. This will become absolute value of x. So this does not match the original. So it's not going to be symmetric to the origin. All right. Even and odd functions. So an even function is going to be symmetric to the x-axis. This is something I want to highlight because it's so important. So this is visually, let me just do it with this because it's way better than my shaky hand. So visually, we can expect to see that. So let's talk about this part right here, because this is the definition of an even function. When you get into trig or you get into calculus and you use this definition of an even and an odd, they want you to know this, okay? All right, so the way that I remember this, because, you know, if you don't start relating stuff to your prior knowledge, it just gets too much to memorize, okay? So in my mind, I remember this with two really quick examples. These are all in my brain, okay? And I hope that by the end of this course, they're on your brain too, you guys, okay? X squared versus x cubed. These, I feel like that's not straight. There we go. I think I made it worse, but I'm gonna move on. So x squared looks like this versus x cubed, which looks like this. Okay. Well, notice that x squared, this exponent, even, and for x cubed, the exponent is odd. And notice that what's the case for this function? It's symmetric to the y-axis, right? Symmetric to y. I'll probably just type it so I don't have to try to write neatly. Okay. And then if you look down here at this other one, this one is symmetric to the origin. My writing's pretty bad and drawing's pretty bad, but you know, if you have imagination here, you can see that this is going to be the same right side up as it's going to be upside down, right? We snapped a picture of just this piece. It's going to look the same right side up as upside down. Okay, so we did rotate 180 degrees. Okay, now that's how I'm going to remember on a test that even functions are symmetric to the y and odd are symmetric to the origin. When you get into trig, you'll probably remember sine and cosine. Okay. Now, the definitions of even and odd, I kind of remember using the same graphs, right? Whether or not, just bear with me, I'm going to call this guy x and I'm going to call this guy negative x, okay? Which, let's assume x is greater than 0. Okay. All right. Then this distance is supposedly, if I drew this properly, let me try to draw it a little bit better, you guys, so you can see what I'm talking about. Probably should have graphed it, huh? Let me do this. Let me make that same. Oh, I know why it's not really lining up. My x needs to be more this way. And I need to fix the graph. Okay. So this distance here and this distance over here, they should be the same whether it's negative x or positive x. Okay, I definitely should have graphed that. But hopefully you can see, right? If I go over x, it's going to be up a certain y value. And if I go negative x, that's going to be up the same y value. Okay, so you can see that this f of x is equal to this f of negative x. Okay. Now, if you look over at the odd one, so let's say that I pick a point, maybe this point, and then his buddy point, right? Okay. This distance right here at x, it's not going to be, it's the same distance. I shouldn't say distance. This y value here, it might be like, I don't know, +2, for example. But we know this y value isn't going to be +2. It would end up being like -2, right? So f of x is not going to be the exact same as f of negative x, right? The way that they'll differ is f of x is going to be the opposite. F of negative x, sorry, I want to write it like they have on here. F of negative x will not be exactly the same. It's going to be the opposite. So I'm going to put a negative in front of it. So up here, they straight up equaled each other. F of x, f of negative x, they are equal. They're both going to be like positive 2, let's say. But over here, f of x and f of negative x are not going to be equal. They're going to be opposite in sign. We went up, so this will be positive. We went down, so this will be negative. So that's why we tossed a negative out front. That's the way that we show, hey, they aren't going to equal each other. They're going to be opposite of each other. Okay? So hopefully that helps make sense, helps lock it in your brain, and gives you something that you can draw on a test so you remember it forever. All right, determine if the function is even or odd. Well, we have to check the symmetry, okay? So since this is symmetric to the, let's pause and see if you can finish that. Since this is symmetric to the, hopefully you said y-axis, okay? This is even. Okay, so remember we said x squared. So this is symmetric to the y-axis divides it, just like our example of x squared, right? And this is even. That's how I'm going to remember that it's even. All right, let's check the next one, see what it holds. Oops. Let's see what this looks like. Okay, this one's definitely not symmetric to the y. It's also not symmetric to the x because we would expect like a point like this to come down and end up around right here, right? That would be symmetry to the x-axis. So this is symmetric to the origin. When I look at it right side up right now, so there's this little hump up here in quadrant 2. If I flip it, I'm still going to get that exact same hump in quadrant 2. This will look the same right side up or upside down, okay? So since this is symmetric to the origin, it is an odd function. So let's go ahead and check to see if this function is even, odd, or neither, okay? So we'll use the technical definition of even and odd just because I know that when you go on to further classes, they're going to speak this language, so you'll want to know it this way. So we're going to start off by checking if it's even, which means that we're going to substitute in a negative x, and we want it to equal the original. When we get to odd, we're going to substitute in a negative x, but we want it to equal opposite the original. All right, so let's go ahead and do the math here. Let's see what happens. Okay, so we're going to substitute in a negative x, okay? All right, so a negative times a negative times a negative times a negative, it's going to be a positive. Anytime it's an even exponent, it'll be positive, x to the 4th. I'm going to bring down this negative sign. And then a negative raised to an even is going to be a positive again. And this is just the original, right? This is f of x. It totally matches. So we can say that f of negative x matched f of x. So that means that this is an even function. All right, now that implies that it cannot be, well, it doesn't imply that it cannot be. Well, if they're functions, yes. All right, I'm just going to go ahead and go through the math here. So let's go ahead and try to see if it were odd. Okay, let's see what we got here. So we're going to be substituting in a negative x for x, right? Which we already did. You know what? I'm not. I'm just going to say it's either even or odd, right? When it's a function, okay? It cannot be both. Now, you're like, what are you talking about, Mecklenburg? Okay. Some of the graphs we had earlier, like maybe something like this, say a circle, just to make an easy example. That is symmetric to the y-axis, and it's also symmetric to the origin, but it's not a function. We're talking about functions here, you guys. It says determine if the function is even or odd. This isn't a function because it doesn't pass the vertical line test, right? Okay, if we were to draw a vertical line, we would touch twice. So as long as we're talking about functions, you guys, it's an either or case. Either it's even or it's odd. Kind of like numbers, right? Hey, either the number's even or the number's odd. You're not going to find the number being both. Yeah. Oh, now, by the way, what the graph of this looks like, let's go check it out. Apparently, this is supposed to be symmetric to the y-axis, you guys. So let's go see what it looks like. Okay, it was x to the fourth minus x to the second. Now, was it plus 2? I don't remember. Let me go back and check really quickly. It was plus 2. All right, so look at that. That is most definitely symmetric to the y-axis. So I think we did a good job here when we called it even, right? I'm gonna put a little comment below it. It is symmetric to the y-axis. So it is. All right. Try it again. So remember, if we're checking for if it is even, we're going to substitute in negative x. We always do. But we hope it matches the original. Versus if we're going to see if it's odd, we're going to substitute in a negative x and hope it's the opposite of the original. Okay. All right. So let's go ahead and substitute a negative x in for x. All right, negative raised to an odd stays negative. Right here, we're going to take this minus a negative and make it a plus. Now, the question is this the opposite of the original? This is not the opposite of the original, right? It doesn't match the original, and it's not the opposite of the original, right? Okay. Opposite. The reason why I'm asking both is because that's what we're looking for. It's like, okay, when we plug this negative x in, does it get me the original back? Or when we plug this negative x in, does it get me opposite the original? It's not getting us either, right? Okay, so we're going to go ahead and say it's neither. So it's neither even nor odd. And I feel like I should maybe shorten this up a bit so I can just put that in the middle of all of them. Will I be able to? Yes. Oops. Okay. All right. Grab, forgot it's not letting me grab. Oh, it did let me grab this text box. Cool. Okay. All right. This doesn't match the original, and it's not the opposite of the original, so it's neither even nor odd. All right, let's go ahead and check. So if we're checking to see if it's even, okay. Sorry for the repetition. No, I'm not. Repetition's great, right? For even, we're going to substitute in a negative x and hope it matches the original. For the odd, we're going to substitute in a negative x and see if it's opposite the original. Okay. All right, so we're going to substitute in negative x. I probably should have just been putting this in the middle the whole time. All right, so let's see here. Negative x cubed minus negative x. Well, a negative cubed stays negative, and it'll be x cubed. And then these two negatives are going to become a plus. And if you look at that, that does not match the original, right? It doesn't match the original. Okay. It's the exact opposite of the original, right? In other words, if we factored a negative out of it, it would match the original. So what that's saying is that it's really going to be negative sign, right? Bring down a negative sign. And then another way that we could call x cubed minus x cubed minus x is f of x. So we could say this. So what we found out is that f of negative x equals negative f of x. And you don't have to go this far. I go this far so people can see this in action. But as soon as you see that this has the exact opposite signs as the original, be like, boom, it's odd. Okay. So this is going to be an odd function. So in other words, symmetric to the origin when we graph it. All right, so let's go look what the graph looks like. X cubed minus x. Oh yeah, that's definitely symmetric to the origin. That's our classic example, right? We go almost all the way to 3. There we go. Look at that. Perfect, right? Right side up, upside down. That's the same exact graph either way, right? It is symmetric to the origin, so it's odd. Cool. All right. Now, I'm going to point this out. Maybe you noticed it, maybe you didn't. But on some of the examples where all of the exponents were even, then the function was even. I'm just looking at that first sentence. So let's go back. Look at our examples. All of the exponents were even on this, so it was even. Let me snap a picture. Bring back the examples here just to kind of show you what I'm talking about. Now, you do have to consider that there is an x after the 2. It is an x to the 0 power right there. So all of the exponents are even on this polynomial, and so that's what makes this even. Okay, so I'm going to circle all the exponents just to make it really clear. Let's go to example B really quickly. Example B. On this one, with the 3, and us adding that x to the 0, because everything has to have an x, well, this one got us a neither. Because if you look, we got odd, and then all of a sudden we got even. Okay, so this one was neither for the answer to part B. Let's just go double check. This doesn't match the original, and it's not the opposite of the original, so it's neither. Okay. All right, let's go look at our last one. So on this one right here, all of the exponents are odd on this one. We add in the 1 right there, and we circle all of our exponents, then this is going to be odd since all the exponents were odd. So if I ever give you a polynomial, then you can just use this trick. This is where the name comes from, you guys. Why a function is called even or odd is based off of polynomials. But I do want to point out, for the example right here, consider absolute value of x. that it doesn't work for things that aren't polynomials. So f of x equals absolute value of x. While the exponent is 1, this is actually an even function, because if you were to graph it, it would be symmetric to the y-axis. So this is an even function. So be careful. This using the exponent trick only works on polynomial functions. It doesn't work on other functions that are not polynomials, okay? And you could even use the plug-in. We know it's even because if we were to substitute in a negative x for the x, right? We just got done learning that this is the same as this, which is f of x itself. So f of negative x equaled f of x. That's the definition of even, you guys. Okay, so this is an even function, but it does have an odd exponent, but it's not a polynomial. So as long as I give you polynomials, or your teacher gives you polynomials, just look at the exponents done. Okay, but for any other function, when you get into trig, they'll have sine, cosine, tangent, and they'll ask you whether those are even or odd. You're going to have to use these definitions that we learned, like f of negative x is f of x, or f of negative x is negative f of x. So you really want to lock these right here in your mind, which ones go with even and which ones go with odd. All right, you guys, that's all we have. Really important section for those of you continuing on. We use this when we're integrating in calculus to sometimes make our integrals easier. This is definitely in trig all over the place. So if you're planning on continuing on, make sure you really pay attention in this section. All right, you guys, thanks for joining me. Take care.